The final experiment in stage 3 was to arrest the aging process in rats. The nanobots attack free radicals, repair DNA, stimulate hormone production, even replace calcium in bone tissue. Since the nanobots have been given to the rats, they haven't aged a day. We've totally arrested the aging process. Did you say they repaired DNA? Jamie asked, his interest suddenly piqued. That's right. Repaired. They use redundant enumeration and comparison to build a clean DNA paradigm. After approximately 10 million iterations, they reconfigure themselves into DNA groups, each with its own strand. Then they replicate themselves and replace all the dirty DNA in the cells. Of course, that's only the DNA aspect of the project. Cellular repair was much tougher to implement. How do you get these robots into the rats? Do you have the rats swallow them? Ben smiled and said, nothing that complicated. We just put the bots in a syringe with some saline solution and inject them into a vein. The bots take it from there. May I see them? Asked Jamie excitedly. Well, I'm really not supposed to let unauthorized visitors into the lab, but since you're a full professor here at the university, I think we can overlook the regulations. Come on, I'll take you down to my lab. Jamie found the electron photomicrographs of the bots fascinating. Is this them? He asked. That's them, Ben said proudly. But I don't see any appendages. How do they do it? How do they make DNA? He asked with a puzzled expression. Nothing as crude as hands, I'm afraid. Look at the convolutions on the surface of the crystal. Each of the peaks and valleys is a binding site. The general structure is determined by the bot's initial programming. As the bots replicate, the structure is modified to attract specific molecules. See those bumps on the sides of the valley? Those are active zones. They allow the bot to attract and bind other molecules to the work molecule. That's for mass production molecular repair. For nonspecific, low-output manipulation of molecules, there's an atomic tweezer on one node. The other side is the reproductive nodule where the bot can reproduce itself as necessary. Do they communicate with each other or does each act independently? They communicate electronically with each other via the blood. The technique was developed in the 50s by the Russians to enable spies to use lakes and surface water reservoirs to make a single untappable electronic connection between agents separated by a large expanse of water. I've developed a more advanced version of the technique to allow the bots to form a peer-to-peer network inside the body. Each bot operates independently, but reports its findings via the net. How are they powered? By the body itself. The bots are able to use heat, ATP, and glycogen as power sources. Electrical energy is obtained from the ions in the blood. Electrically, they're 100 times more efficient than a nerve cell. You said they were heuristically programmed. What does that mean? Jamie asked, fascinated by the concept of millions of molecular robots operating semi-independently to repair cellular damage. They are given a general set of instructions in their original program. As they find discrepancies between the program and the body they are in, they modify their instructions to match their environment. In short, they figure out what's wrong and how to do it. Then they go out and make the repairs. Well, what do you think? This is fantastic. When will they be ready to give humans? Asked Jamie enthusiastically. Humans, Ben laughed ruefully. Not for a good many years, I'm afraid. We have years of testing ahead of us. But think of all the lives that could be saved. Ben shook his head. We have no idea what they would do in a human. Even though the DNA module would work, the programming for the hormones would probably be radically different. If we were testing the effect of the bots on another type of lab animal, we'd rely on the heuristic programming features to reprogram the bots. We couldn't take the chance on humans. There might be odd side effects.